Now we have already introduced most of the low-level low-level multimedia analysis. What I say low-level means we start from the signal of the given data, no matter image, video, or audio. We extract features, and then we discover the underlying structure or the characteristic of features to understand what are embedded in the multimedia content. However, for human beings, we are not work based on such signal characteristics. We are more perceptible. We are more familiar with high-level semantics. So from the early year of year 2000, more and more study try to move from the low-level analysis to high-level semantics analysis. And in the following materials, we will describe the basic idea of semantic concept detection, especially in visual content. And the difference between low-level structural analysis and the high-level semantic concept analysis is that there is a big gap between two types of study. And this gap is called the semantic gap. Okay, the semantic gap problem is the most notorious or the most significant problem in computer vision, image processing, and multimedia information retrieval. So what is the semantic gap problem? Okay, that is the lack of coincidence between the information that machine can extract, between the information that the machine can extract from the multimedia data and the interpretation the user may give to the data. Okay, so this is the difference between the feature characteristic and user understanding. Okay, so this is a problem about the semantic gap. Given a sequence of baseball video, okay, and we may see there is a picture picturing the ball, and then the ball is hitting to the outfield, and then the player standing on some base. Okay, and another sequence is also a pitch view, and then an outfield view, and then the player, the runner, occupy some base. Okay, these two sequences are quite similar because they have very similar visual appearance. They have similar audio features. Okay, but the meaning of these two sequences may be different. For example, this one, for the first sequence, this player issue a single, and this player issue a double. Okay, and for single and a double, they have different meanings. If you understand baseball games, we will know that double is more important than single because double is highly probable, is more probably issue a score. Okay, so although the visual appearance, the visual evolution of these two video sequences are quite similar, they have different semantic meaning. And this is one example of the semantic gap. Therefore, for semantic concept analysis, we have to do analysis from features to semantics. Okay, the features are data characteristic that can be directly computed from content or from a signal, like audio feature, energy, zero crossing rate, or video feature like color, motion, and age. However, the semantic concept is the meaning of the content, like the home run in a baseball game, the gunplay scene in an action movie, and so on. So it's not easy to detect a home run just based on the color, motion, and age. Okay, it's not easy to detect gunplay scene if we just we just examine the audio energy or the zero crossing rate. Okay, it will not be easy to do so. Therefore, we have to devise new model, okay, to do semantic concept analysis. And in the following material, we will introduce a very basic but a very pioneering work about semantic indexing of multimedia content. And this paper was published in year 2003 in EuroSIP Journal on Applied Signal Processing. And this system was constructed by IBM T.J. Watson Research Center. And at that time, the IBM holds the pioneering role in semantic concept detection. What is the motivation of this work? Because we already know that we can do content-based image retrieval. We may also do content-based video retrieval. Okay. However, query by example may not be suitable for user, and because users are more familiar with query by keyword. So imagine, although we are right now we can do content-based imagery retrieval or query by example in Google, but how many times you use such retrieval in Google? Okay, you are more familiar with typing keyword to find interesting images, right? So this work facilitate query in terms of a limited vocabulary of semantic concept. If we can recognize the concept or recognize the keyword of a given image or a video, then we are able to do query-based image retrieval or video retrieval. So this is the main motivation of why we still have to do semantic concept detection. And this works approach semantic labeling as a machine learning problem. And at that time, in year 2003, machine learning technology have just emerged. So at that time, this paper would be one of the most pioneering work by applying machine learning technology in multimedia content analysis. And then they try to begin by assuming a set of atomic semantic concept that is very basic, simple semantic concept like object, scene, and event. And then multiple atomic concepts may be combined to define high-level concept. So the idea here is quite important. This would be one of the earliest work to propose such idea. We combine atomic concept to form a high-level concept because it's very difficult to detect very high-level concept based on audio or visual feature. So we transform our task into, we first detect very basic concept and then combine the distribution or the occurrence of such basic concept to form high-level concept. The set of atomic concepts are annotated manually in audio, speech, and video within a set of training video. Therefore, they have to define atomic concept first. And then the annotated training data is used to develop statistical model for atomic concept. And each such model can then be used to automatically label occurrence of the corresponding concept in new videos. Okay. Therefore, they use a statistical model to detect atomic concept. To detect high-level concept, we also need another complicated statistical model to construct and combine information from existing atomic model. And the challenge of such work is that the low-level feature appropriate for labeling atomic concept must be identified. So what kinds of features are more appropriate to detect the defined atomic concept. And the appropriate scheme for modeling these features are to be selected. So what kinds of model, what kinds of statistical model, what kinds of method are more appropriate to model such artificial features? The second challenge is high-level concept must be linked to the presence or absence of other concepts, and the statistical model for combining this concept model into high-level model must be chosen. Okay, so when we try to construct the high-level model, we need to consider the distribution or the presence or absence of other atomic concepts. The third challenge is the information from multiple modality must be integrated or fused together. Okay, and fusion could occur at various levels, like low-level features, or maybe by combining the atomic concept, or by combining several atomic concepts. Okay, and this atomic concept may be visual atomic concept or oral atomic concept. And this paper focuses on modeling atomic concept and on the representation of high-level concepts. Based on the idea mentioned above, they propose the following overall framework. Basically, they develop tools for defining a lexicon, that is the set of semantic concepts we will detect. And then they also adopted machine learning technology to learn the models to describe the atomic semantic concept. And then they also developed tools to support data retrieval. And this is the illustration of the whole framework. So given the media collection, they developed an annotation tool to annotate the ground truths of semantic concept. And based on the media collection, they will do visual segmentation and extract visual features and audio features. And then they develop several models to detect audio atomic concept, speech atomic concept, and the visual atomic concept. And in the retrieval model, they fuse the results of these models and then do the media retrieval or semantic concept retrieval. So first, the lexicon of semantic concept. The so-called lexicon is similar to the dictionary. If we define the dictionary, that means we define the set of semantic concepts we will try to model and detect. So here, the lexicon of semantic concept define the working set of intermediate and high-level concept covering events, things, and objects. And although it's difficult to impose a strict hierarchy on semantic concept, some of them can be defined directly, while others can be defined in terms of a set of concepts, like the atomic or simple concept, sky, music, water, speech. All these are simple and can be defined directly. But some concepts are more complex, like parade. Parade may need to be described in terms of a collection of people, a particular types of accompanying music, and maybe working toward the same direction, and so on. Therefore, we can use some atomic concept to model or to describe a complex concept. And this is an illustration showing the state, at that time, the state-of-the-art media annotation tool. You can see here, given a video, they can do video shed change detection, and then they can extract keyframes. They can also show the audio, the corresponding audio signal. And by collecting some keyframe of the video or selecting a range of the audio, they can do some annotation, like from this time instance to this time instance. there are some sound effect in this period, and there are some visual concept in this period, and we can also define some keyword. Okay, therefore this annotation tool plays fundamental rules to facilitate such study, because when before we start to do concept modeling or define concept, we have to define the ground truth, the training data, such that we can adopt machine learning technology to do automatic detection. Then the learning part, how can they learn semantic concept from feature? Okay, from atomic concept are model using feature from a single modality. Okay, so atomic concept just come from audio, or just from video, okay, or just from speech. Okay, and the integration of cues from multiple modality occur only within models of high-level concept. Okay, and how can they integrate multiple atomic concept to be a complex concept? There may be two types of fusion. One is called early fusion, another one is called late fusion. The so-called early fusion is that we will fuse at the feature level. Okay, so imagine that we have a video, and now for each video we can have many video frames, as well as the accompanying audio sound. Okay, and we can detect visual atomic concept from video frame. We can detect audio atomic concept from audio. Okay, and then how can we fuse them? One way, the early fusion, is we just concatenate visual feature with audio feature. So this is called fusion at the feature level. And the late fusion is we fuse at the model level. That means for a visual feature, we detect what kinds of atomic concept in the video. For audio concept, we detect audio concept from audio signal only, and then we fuse visual concept and the audio concept at based on the result of atomic concept detection. Okay, and this works employ a late fusion approach for combining modalities. Since the unit of retrieval is a video shot, and the effort has been focused on fusion in terms of shot. Okay, so the unit of retrieval is video shot, and this is why we introduced video shot change detection in the very early stage of this class, because it is the most fundamental process to do video analysis. And how do they model the high-level concept? They consider two categories of machine learning technology. One way is called generative model. Another way is the discriminative model. And these two models has been introduced when we talk about the machine learning technology. So remember, the generative model is conceptually we assume there is a model behind the realistic items, like we assume there is a model to describe the sky object, or to describe the bus object. Okay, and the generative model is we try to estimate the parameter that are used to describe the generative model. And for discriminative model, we don't assume there is a backend model that can be parameterized by some parameters. We just take the data directly and try to separate or classify the given data into different classes. So first, we will introduce the generative model. Okay, and in this paper, the generative model is implemented based on probability. So the probabilistic model is used to build the generative model. Okay, they try to model a semantic concept as a class conditional probability density function over a feature space. So, for example, from video frames, we can extract a lot of visual features, and given a sequence of visual feature, we will try to estimate the class conditional probability given the visual feature, okay, such that we can know the event number one, the probability of event number one given such visual feature, the probability of event or the concept number two given the visual features. Okay, and we choose the label as the class conditional density, which result in the maximum likelihood of the observed features. So this idea is totally the same as what we say in audio sound effect. No, in audio classification. Okay, in that time, we have a model to describe environmental sound, to describe music, or to describe speech. And given an audio signal, we extract audio features and input these audio features to these models. And each model can output a likelihood of such feature, the likelihood of generating such features. Okay, and we just select the model that generate the maximum likelihood value. Okay, and here they use Gaussian mixture model to describe the independent observation vectors. And if we consider the temporal, if we consider the concept that has time evaluation, we will use hidden Markov model to describe the time series data. Like we may consider people walking, the sound of people walking, the sound of applause, the sound of laughter. Okay, so we can use hidden Markov model. And from now, we can also understand why we introduce the audio content analysis before. Because right here, when we enter the age of semantic concept detection, we will use all the technology and all the concept we introduced before. Okay, so here we use the idea of using hidden Markov model to detect audio semantic concept, or maybe Gaussian mixture model to detect a static visual or audio atomic concept. And here are the formulation of Gaussian mixture model and the hidden Markov model. And you can just recall that given this model, the probability of such feature generated by this model is given by this likelihood value. Okay, and this likelihood value can be described by the weighted sum of many Gaussian mixtures. And this is the formulation of an hidden Markov model. And given this model, such model generate a sequence of features. Okay, is this probability, and this is also a likelihood value. And you can see that this is the transition probability, and this is the observation probability. Okay, and all this concept has been introduced before. In this paper, they also use discriminative model. In that time, they adopt the support vector machine. Okay, so right now you can also imagine why we introduced support vector machine before. Okay, at that time, at year 2003, support vector machine was just emerged. Okay, and they at that time SVM was the state of the art technology to do machine learning. Okay, so they first briefly introduced the concept of SVM, And SVM tries to find the best fitting hyperplane that maximizes the generalization capability while minimizing misclassification error. And the SVM maps samples to higher dimensional space and finds suitable linear hyperplane separating two classes. And linear hyperplane in the high dimensional space results in a non-linear separation surface in the kernel feature space. So these were all introduced before. Okay, so yeah, so this part is the kernel tree, right? You can use kernel tree to transform the original data to a higher dimensional data, and you find linear classifier in high dimensional space. And then when you go back to the low dimensional space, this linear classifier becomes nonlinear classifier. Overall, they learn static visual concept or object using Gaussian mixture model. For events and objects with spatial temporal support, they use hidden Markov model because, as we know before, hidden Markov model are more appropriate to describe features with time temporal evolution. And they try to model the time series of the feature vectors of all frames within a shot. And in this paper, the author compared the performance of Gaussian mixture model and the support vector machine for the classification of static scenes and objects. So in addition to model static scene and objects by Gaussian mixture model, they also try to model by SVM. For audio concept, the audio-based atomic concept may include silence, rocket engine explosion, music, and so on. And the hidden Markov model is used to model each audio concept. And the detection scheme is that in a shot, they will use hidden Markov model to generate an n-best list at each audio frame, and then average this score over the duration of the shot. Therefore, for every audio frame, they will generate a list showing the most probably audio concept, and then by consider a sequence, by consider a duration, a period, maybe 10 seconds or 5 seconds, they average this score over the duration of the shot. Okay, and then do some normalization, and finally they can determine which audio concept is most probably occurring at this duration, in this duration. They also especially consider the speech information. At that time, in an early 2000, IBM has the best speech recognition engine. So they will use their state-of-the-art speech recognition engine to transform the speech signal into text. Okay. Speech cue may come from manual transcription, such as closed caption, or the result of automatic speech recognition. Okay, they can do both. The words corresponding to a shot or words occurring symmetrically around the center of a shot are the speech cue of this shot. So, what does this mean? For example, given this shot, maybe the duration of this shot is here, and then we can recognize the speech, the spoken word. We can recognize the word spoken in this duration, and all this word can be used to describe this video shot. But it's often that the word spoken nearby this shot is also very related to this shot. Okay, therefore they also try the so-called symmetric scheme. They also try to recognize the word spoken before this shot and after this shot, and then use all these words to describe the center video shot. Okay, and this is the so-called symmetric scheme. They also do some word processing, like they do tag with part of speech. Okay, the so-called part of speech is verb. Try to discriminate each word into verb, noun, or maybe adjective. Okay, and so on. They will also do morphological decomposition. That means we will transfer, like processing. Okay, the original form of processing should be processed. Okay, so the so-called morphological decomposition is we will transform a given word into its original form. Okay, like using. The original form of using should be use. Okay, so this is called morphological decomposition. And also, they try to eliminate a stop word. The stop word means they occur very frequently, but they don't have specific meaning, like the word is, to, us, and so on. Okay, they happen very frequently, but they don't have specific meaning. Okay, and they will use the most frequent word occurring within shots to represent shots. Okay, so not all the words, they just use the most frequent words, maybe just a subset of these words to describe this video shot. And the information mentioned above are all from a single modality. Okay, and how do they learn multimodal concept? Okay, each atomic model generates score from a single modality, and for high-level concept, they try to fuse the detection results of semantic atomic models. They try to model interrelationship between atomic concepts, which may not be possible if we don't do low-level feature. Okay, if we don't detect atomic concept in advance, and it is not possible if we model just based on the low-level feature. That is not possible. Okay, so the feature is at the high-level concept labeling modeling. The feature is the score obtained from atomic models. So we will aggregate, like aggregate the score of sky, the music, or the rocket. Okay, we will aggregate the score for all these atomic concepts, and using such score as the feature to construct the high-level concept modeling. And the method they use is include Bayesian Network and a support vector machine. And in the evaluation, they will try to compare the performance of these two approaches. The Bayesian Network allows us to graphically specify a particular form of the joint probability density function. And the score from each intermediate concept are assumed to be conditionally independent given the concept's presence or absence. And basically, Bayesian Network is a very generic model. And if you are interested in such technology, please refer to related works. Okay, and right here we just briefly introduce the idea. The parameters for the model can be estimated from the training data. So basically, we will try to find the joint probability of an event and the corresponding atomic audio concept, visual concept, and the text. Okay, and this probability can be described by such formulation, because given this event, we will get some audio concept, video concept, and the text. Okay, and right now we try to infer the probability of such event given such audio, video, and the text concept score. Therefore, by given such graphical model, we can estimate such joint probability by the prior probability of such event and the conditional probability of given such event, the audio concept happening. Given such event, the video concept happening. Given such event, the text happening. Okay, and we multiply all this probability together to estimate the joint probability. And this is the idea of Bayesian network. And of course, details of Bayesian network are much more complex. And please refer to related works. We can also aggregate multimodal concept score by SVM. Okay, we can simply aggregate, concatenate the audio score, video score, and text score as a vector, and then we can view such vectors in a feature space, and using SVM to discriminate the concept score vectors into several defined high-dimensional concepts. Okay, so here the score from all atomic concept classifier are concatenated into a vector, and SVM is used to classify these vectors. Therefore, from the introduction mentioned above, we can use SVM to model static concept. We can also use SVM to model high-level and a complex concept. Okay, so the difference is for modeling the atomic static concept, the input is the low-level features. For modeling high-level concept, the input is concept scores. In the following, we will describe the experimental results. The corpus they use, the corpus is the word corpus is the data set or the collection they use in evaluation. They use Traffic 2001 corpus, which comprise production videos derived from NASA and the Open Video Consortium. Okay, and it consists of 7 videos comprising more than 1,000 video shots. And this is very early years. And right now, we have hundreds or thousands of videos, or more than 10,000 videos in the traffic corpus. Of 78 manual label rocket launch shots, only 51 contain speech, and only a subset of those contain rocket launch related words. Okay, and this sentence is used to clarify that we may imagine that if there are always some anchor person speaking the status of the corresponding video, then how should we do the visual processing? Okay, but here you can see we cannot just rely on the speech information. Okay, because only part of them include speech information, and only a subset of them are content rocket launch related words. So you cannot just rely on speech information. We have to do audio content analysis and the visual content analysis. And music and the rocket engine explosion found in 84% and 60% of manual label audio samples. And in the visual side, the rocket shot are from a variety of posts. Therefore, it's not easy to detect whether there is a rocket inside. And the predefined lexicon is for visual concept. They define rocket, object, fire, smoke, sky, and outdoor. For audio concept, they define rocket engine explosion, music, speech, and noise. For multimodal concept, they define rocket launch. Therefore, we can see that this is a very small data set. They just define a limited number of lexicon, the limited numbers of atomic concept and a complex concept. Okay, but this was done in very early years, and right now we have many more than thousands of semantic concepts can be detected. But the paper is still worth reading because they propose the very early idea in semantic concept detection. The features they extract. The visual features they extract include HSV, color histogram, age histogram, and the shape. The audio features they extract 24-order MFCC. Okay, so again, we can see the effectiveness of MFCC. In this work, they just use MFCC and excluding other timbral features, audio features. The evaluation matrix, they adopted 7-fold cross-validation. So remember that we have a data set, and we can separate this data set into 7 equally divided subset. Okay, and from them, 6 of them are used for training, and 1 of them are used for testing. And this is called one run. And we repeat this training and testing procedure for 7 times. So this is a 7-fold cross-validation. And then they use the precision recall curve to measure the retrieval performance. In addition, the overall figure of merit (FOM) is used to summarize the performance. The definition of FOM is the average precision over the top 100 retrieve document, and we also call it precision at 100. Here is the accuracy of visual concept classification. When they model the visual concept by Gaussian mixture model, they use 5 Gaussian components. Okay, and then if they use the discriminative classification, they use SVM. Okay, and from this table we can see from this concept outdoor, sky, rocket, fire, and smoke. When they use SVM, the accuracy around 0.97. Comparing to 0.86, okay, for the outdoor concept. For the sky concept and for the rocket and fire smoke, we can also see in these 4 cases, SVM outperform Gaussian mixture model when they try to define or when they try to do such a static concept detection. And this is the precision recall curve corresponding to 4 different concepts. The first one is the outdoor concept. Okay, and you can see the green curve is from Gaussian mixture model. The red curve is from SVM. The x-axis is recall, y-axis is precision. And it's clear to see that the SVM performance is significantly better than Gaussian mixture model. And for the sky concept detection, we can also see this track. And for a rocket, this is rocket, and this is for fire and smoke. In all these 4 cases, SVM outperform Gaussian mixture model. And at that time, in early year 2000, SVM just emerged, and many studies demonstrate the significant performance improvement given by support vector machine. And this paper verified this trend again. So for the concept outdoor and the sky, when sufficient numbers of examples is available for training, the SVM classifier lead to a very accurate retrieval performance. And even with small numbers of examples, SVM classifier still provide reasonable, accurate detection performance in rocket and fire smoke. So SVM outperform Gaussian mixture model in modeling static visual concept. For modeling the concept with time series data, okay, they will compare the 5-state left to right hidden Markov model with Gaussian mixture model in detecting the rocket engine explosion. So such audio concept is a time series. Okay, and this is the precision recall curve obtained based on Gaussian mixture model and the hidden Markov model. And here we can see the the hidden Markov model outperform Gaussian mixture model, and this is not surprising because GMM cannot describe time series data, but HMM can do. And this table shows the performance of several audio concepts, the accuracy of detecting several audio concepts like a rocket engine explosion, music, speech, and speech plus music. And the FOM is 0.38, 0.92, 0.89, and 0.76. And as obviously, the performance is content dependent. Some simple audio concept can be accurately detected, but for complex audio concept, the performance is not so good. We may imagine that how if we just use speech recognition to do retrieval. So here we will compare retrieval performance based on manually produced transcription with transcription produced using automatic speech recognition. And at that time, the automatic speech recognition error rate is about 29%. And then they evaluate two schemes. The first scheme is document compressing word corresponding to a single shot. The second scheme is the so-called symmetric scheme. Documents as the 100 words symmetrically center at the center of each shot. So as I said before, there is a shot here, and at the center, maybe here, we will look at the 100 word spoken before this time instant, and the 100 word after this time instant, and then we will use all these words to describe this shot. Okay, and they perform two types of query. The first one is called the training set based query. That means that we just limit to use the word that once appear in the training data, like engine, flight, lift off, NASA, 5, 4, 3, 2, 1, and the shuttle space. Or we just give the subject the task. Okay, we just want you find the rocket launch video. So how can you post your query? So the second strategy, the second scheme is the human knowledge based query. So human can issue the query as their will, okay, according to their knowledge. So there may be some keyword: NASA, rocket launch, space, agency, satellite, spacecraft. Okay, so agency, satellite, spacecraft may never appear in the speech data in the training set. And this is the result. Precision recall curve. We can see they evaluate the manual speech spoken word with the short scheme, the manual spoken word with symmetric scheme, the automatic speech recognition with short scheme, automatic speech recognition with symmetric scheme. And you can see the performance and recall are all similar. Okay, and we can see the FOM value. Basically, they are similar. They are not so accurate. Okay, there may be some benefit from further improving the automatic speech recognition performance, and very low recall rate. That means here, at very low recall rate, the automatic speech recognition short scheme outperform the ground truth short scheme. Okay, but this may not be this may not make a very solid conclusion. So this is just for your reference. So the evaluation mentioned above are all for atomic concept. Okay, but now how about the multimodal concept or the high level concept? Okay, Here is the result based on Bayesian network. Okay, a Bayesian network is to combine the solved decision of the visual classifier for rocket object with the solved decision of the audio classifier for explosion, and then they can find rocket launch concept, not rocket launch. Here they compare if the Bayesian network just using the visual concept, just using the audio concept, or using both audio and video concept, and we can see that the Bayesian network perform much better than either audio or visual model alone. Okay, so this result suggests us we have to combine, we have to integrate audio information and visual information to detect a high-level concept. And this is the result obtained by SVM. Okay, if we combine audio and visual information, we get better precision recall result. Okay, so score of all atomic models are concatenated as a 9-dimensional feature vector, and they do cross validation and 1XO approach. Okay. This table shows the FOM result for unimodal retrieval and then the two multimodal fusion model. So this is the best unimodal result, 0.56. The best visual result, 0.39. If we just use text information, the FOM is just 0.14. If we use SVM and a Bayesian network, the performance can be boosted to 0.62 or 63. And in this table, we see the performance of SVM and the Bayesian network are similar. And this is the system snapshot. The snapshot of this system. So they can do some query. You can input some query. No, actually, they just handle the rocket launch query. Okay, so if we search the rocket launch, then the top return video shots are here. Okay, order in the list, and we can see that yes, most of them are rocket launch, and these two maybe not, maybe yes. Okay, and so on. So these are the snapshot of this system. And remember, this system was developed around more than 15, maybe more than around 15 years ago. So it's very historical system. But the idea proposed by in this paper just issue very novelty to inspire the following semantic concept detection research. Therefore, we introduce this paper for you first.